And I need to share the entire screen. Okay, so I just completed the conclusions there before we started. I think you can see that, right?
Yes.
Yeah.
Yes.
Yeah. Yes.
Just
okay.
Make it full screen. Make it full screen.
Can you? Is it full? It should be full screen now.
It's full screen,
no,
but
it's not full screen.
Magnify a little bit, maybe.
No.
I mean, it's okay. It's okay the way it is. But if you can magnify, it will be even better. Otherwise, what you had was fine.
Yes, that's okay. Yes.
Yeah, what you had was fine. Actually.
Okay.
Yeah.
Okay. So that's as big as that's as big as it can go,
that's
unfortunately.
Yeah, that's
but
fine.
It's nice
Perfect.
and clear. Yeah.
Great. So this is really the second talk with the same title, Anamorphic Universe Model Hypothesis Research. But in this presentation, we'll be looking more at surface tension gravity, quantum gravity to a degree, and the Marangoni Cosmological Catastrophe. So I'll start with the introduction. And so the objectives or topics of this are, to begin with, as I mentioned already, surface tension gravity, magnetic monopoles, quantum entanglement we'll discuss, electromagnetic gravity unification, quantum gravity, sort of an attempt at that, some of the concepts around it, the idea of changing constants to do with perhaps gravitational constant and some other Planck constants, but also some different ideas. And so the creation of the universe we'll look at briefly, universe structure, the Marangoni Cosmological Catastrophe, and gravity anomalies before we present our conclusions. So a quick review of related work here in terms of surface tension as a model for gravity. We have Himanshu et al. They employed surface tension to describe the tangential pressure of a normal curvature in curved spacetime. So that's a lot to do with general relativity, and it's generally up to the boundary surface of the black hole and that kind of thing. Whereas Callaway kind of did it from the reverse point of view. So he employed density matrix formalism developed previously for studying black hole entropy as a means for evaluating surface tension of fluids. So there's this interplay between the two disciplines, if you like. And part of the reason for that might be because surface tension is measured in similar units to gravity in terms of dyne and newtons. There's also other reasons, such as presented by these two authors Bartholin and Bernard Barbara, I think it is. I thought it was yeah. Anyway, so soap bubbles on the surface of a liquid. So their concept here is that they think the universe is a three-dimensional universe, obviously as a 3D surface of a 4D bulk space. So it's like the surface tension of a liquid. Yeah. There's a 4D bulk space, and then our own space is like the surface. So that's interesting. And then they could you guys mute your audio, because there's a bit of feedback,
yes.
I think.
Okay. Yes. Yeah, of course.
Yes. Distracting. So it's no problem. So okay, so with the bubbles, they're looking at bubbles then on this surface and attempting to research black holes and things of that kind. They also have this idea of fractals, bubbles, and it's interesting, but it's not directly related to our work. So move on. So to begin with, we'll look at surface tension gravity and the motivations behind this. So previous research, as we mentioned, into surface gravity tension models generally restrict itself to the boundary of a hypersurface. So like I mentioned about the black holes, but in as we know, gravity as a three-dimensional force has no such restriction. It permeates straight into the center of solid bodies. So this part of the research presentation will analytically extend the surface tension of gravity inside a body. And this research suggests that gravity becomes stronger at distances closer to the core before becoming weaker again and nullified at the center. And the reason why this is okay, that we're allowed to do this, partly because of something called the Hole argument, which as it states here, allows for topological curvatures of the interior of a gravitational body to be different of those on the exterior. So to begin with, we start with a very simple model of space-time curvature, and we're not using any complicated tensor mathematics here. I just kind of stick to vector functions just to keep things a bit simpler. So we see that we have a vector field f over a linear space, and with a step function of 7, and so it has this general form here creates a pattern that we see in the image. So the vectors are kind of smaller the further out we are, and closer to the surface they get bigger, but they don't interpenetrate into the surface center of the body. So that's what we want to achieve here. And so one way to think about this is if we have a 3D cube submerged in a viscous fluid, the surface tension of that fluid will adhere to the size of the cube. And if we imagine the cube is transparent, we know that the surface tension doesn't go inside the cube, it's only on the outside. But if we have a two-dimensional projection of the cube, it will appear as though the lines cross into the interior of the cube, and in effect the lines hitting the back of the cube there, the smaller inner cube or square, will be pointing towards us, so we won't really see any capillary action there. But if we increase our dimensions from 3 dimensions to 4 dimensions and project into 3, back into 3, then we should begin to see that same curvature inside the cube, which is really the object of this part of the presentation. So to begin with, we start with a series of toy models. First one is in 2 dimensions. So we have essentially we have a sphere, and we have the vector field pointing towards the surface of the sphere, just as we saw in the first image. And what we see is that the surface tension or gravity increases on the boundary of the circle as it's projected to 2D. But we also see that it extends into the center, and this will be the null gravity vector, the very center of like the Earth, for example. But this is the central vector is obviously perpendicular to the 2-dimensional space, so that's why it remains a null vector in that sense. These are just more detailed graphs of the previous one using slightly different display method and the enlargement. Although we see in this case that there is no null vector. So that's a bit strange. Then I took profiles of the vectors that we saw previously, and the problem with this is that it's not a tensor kind of function that deals with every point in space. So we have these bumps that represent the vectors. So we kind of interpolate that, and we see gravity increases towards the surface and then decreases linearly towards the center. And so this is the kind of thing we'd expect from gravity in general. Obviously, it should also decrease as it goes away. So these bumps here are not what we require. But we also notice that there is no, there's no, this is completely normal. So we're still missing any sense of gravity in the center of the object that we were talking about. So what I tried to do then was to move towards the 4-dimensional version. and this is just a perspective projection graph using the same ranges and step functions as before. Just increase the number of vector coordinates to 4, transpose them, and then this is the equation that results in this. But the problem with this is that, again, it's a bit hard to discern what's going on. Obviously, surface tension is getting much stronger on the surface, or gravity, but not in the center. So it doesn't extend to the center really. So in the second version, I used stereographic method, and we see that we do get results, although they are a little bit confusing as well. But there's definitely some sort of structure in the center of the gravitating body, and these are quite strong as well. So it is interesting that the stereographic method, projection method, produces the most interesting results, given that it's been used by myself and others to model various aspects of cosmology, both in the form of the anamorphic universe model we're discussing today, as well as aspects of quantum mechanics. And it also forms the basis of twistor theory, which is kind of Penrose's research, and Peter Voigt has also done a lot of work on that. So taking the previous three-dimensional stereographic projection vector space, or vectors, and doing the same thing, creating a vector field profile, we get a lot more data. Here's the surface, and this is the interior. So we get big spikes just close to the interior as well. We can again try and interpolate that to smooth it out a bit, and the structure remains. So that's kind of a positive result in that sense. Obviously, there's a lot of work to be done on this to improve it, and it may be incorrect anyway that there is an internal structure to gravity. Although if it was true, it would be interesting, such as how does this impact the formation of black holes, or does it? If there is this sort of how do you say oscillation of gravity in the core, do they overlap, or does it all just contract in a uniform way and have no bearing really on black hole formation? So we'll move forward with quantum gravity. I think there's this animation, but it doesn't really matter. So we'll just move on. So to begin with, here we're looking at what I've termed gravito-magnetic gravito-torsiomagnetic monopoles. So the first point that it's worth considering here is to do with and related to quantum entanglement. So if we have the hypersphere here, as we do in anamorphic universe model, and we have the projective point, ordinarily we'd have the projective point at the North Pole, essentially. But if we move it into the center of the hypersphere, and we have the rays coming out of the projective point, obviously, and hitting the hypersphere at either side, and we imagine that so this is the monopole, and as it hits the hypersurface, then it just becomes a point. So a particle, for example, an electron, and we could measure that because it's a torsion wave, in a sense, it spins around. Then if we have an electron on this side of the hypersphere, we could measure it as spin up, but on the opposite side, it would be spin down, and altering the spin would have an instant effect on either side, even if they were separated on distant sides of the universe. So that's another good sort of toy model that we could think of. But if we want to consider a particle like a photon or an electron, and then we're going to beam split it to create an entangled pair, and what we can do is we can route the projective point at the center back up through to the North Pole. So then when we split the two electrons, we see that instead of the line going through, it has to go up and then back down. So there's some sort of like gear mechanism at work in the torsion. But as we can see, it doesn't matter how far away they get, this relationship between the two particles will remain the same, and it will be instantaneous. So I guess some of the implications of this from the point of view of the projective point is that, well, it seems to me that all things are, everything is connected through the projective point. So if we think of, you know, different Eastern philosophies like Buddhism, they say all is one or whatever. You could have it as the projective point. It kind of symbolizes that. It also helps to explain psychic phenomenon and other things like mass hysteria, hive mind effects, and synchronicities, things that are usually sort of, not always, but often outside the scope of science. So another issue, because we're talking about instantaneous kind of transmission of information, if you like, although that's generally precluded, but, you know, or as they prefer to say, spooky action at a distance, so you don't get caught in that trap, I guess. We can also think of gravity as instantaneous. And this model here kind of is a visual depiction of that. It shows an object, obviously like a moon or sun, distorting the space-time metric. And as we'll see in the next slide, it basically happens instantaneously. So it seems to disprove the notion that gravity is limited to the speed of light, at least from a translational point of view. So as the body is moving around, it could, if space was some sort of like viscous substance, then we might see a residual delay in the effects of gravity from a sort of perpendicular point of view. But in general, I think certainly the consensus is that space-time has nothing like viscosity or rigidity, but perhaps that is not the case. So if we, this is supposed to be an animation, but it's not working. Oh, there we go. So we get a better understanding of the instantaneous nature of gravity from that animation, I think. So we'll move on anyway, because it's not really functioning very well. But all of this is kind of related back to the monopole part that I was speaking of in terms of instantaneous data transmission. So if there is data like stars and galaxies on the surface of the hypersphere, which there must be from the anamorphic universe model perspective, then the light coming out of the projective point, once it hits anything on the sphere, it must transmit it instantaneously to the tangent plane. Otherwise, there'd be a delay between events happening on the hypersphere and those on the tangent plane. And seems reasonable to conclude that there would be no delay. Although, yeah, so that is kind of the basis of a lot of this stuff. So, and well, we know because that data could be transmitted instantly from one entangled monopole or particle to another via the torsion effect of the monopole, then it stands to reason that the data can be transmitted from the hypersphere to the tangent plane instantly anyway. And since we're saying that gravity is instantaneous and therefore a torsion effect, we can link the gravity to the monopole. So that's where we get the gravito part. We obviously have the torsion part, and then the fact that it is you know, a monopole as well, because it's just a single line, which is kind of how Dirac initially envisioned monopoles. So so yeah, sorry there. So that is I'll just move on to the next slide. Yeah, so basically with the monopoles as well, that I forgot to mention this, is that you know, they are light, because we're talking about light essentially streaming from the projective point to create the projection. Then it's a light as we know, is an electromagnetic wave. But in the monopole version, we're kind of reversing that and saying that it's a magneto-electric wave in a sense. It's instead of electromagnetism, it's the reverse. So we're looking at Maxwell's equations. For example, here we have Ampere's law in equation 1. But we want to kind of reverse it so that instead of having where you have like electric field creating the rotations in a magnetic one, you might have, so instead of having a straight line electric field with rotating magnetic vectors, you'd switch them around so that the electric field is rotating and the magnetic vectors become straight lines. So that's kind of what we have here in the second equation. We have the magnetic term is no longer in bold because it no longer represents a vector but a scalar because it's intersecting with the hypersphere. And then the term on the left here is the gradient of the electric field, which really in this case would be the gradient of the magnetic field in a sense, but also it's meant to be the gravitational field, which is why we can substitute it with the gravitational field equation. But one thing that Gerd pointed out as well is that the units on this side do not comport with the units on this side. So we can't do anything further than this. We're kind of stuck. So to move on from that, I decided to sort of borrow elements from general relativity and alter the mass terms into like h bar over c times or cubed, I think it is, and then so sort of combine the two, essentially the gravitational field equation and Planck length equation together, so that the units are more compatible, and then we can start to, we can multiply one side by the electric permittivity, and then we just have the charge density on top. So then we can break that up. But that was really as far as I could go with the equation. I did try some other things, but initially I thought I had much better results for quantum gravities. But then as I kept going, I realized there was major problems with the work I'd done, so I had to cut it out of this presentation. But I think it's better to present something that is, well, maybe not as spectacular, but is more accurate. So I'm sure you guys appreciate that. So over here, I'm just using kind of basic units. Just, I'm not really calculating anything specific here. So everything is just, in terms of coefficients, I'm just using ones. So on the right side, we wind up with coulombs per cubic meter, which is just electric charge density. And on the left side, we wind up with reciprocal henries, which is something I've never heard of, or microsiemens per hour, which is apparently electric conductance charge rate. So I'm not really sure how useful that is from a point of view of quantum gravity, but maybe more research in future will shed light on that, or I might have to take a different approach in future. So let's look at something that's a bit more solid or tangible in terms of electromagnetic gravity unification. So this is what is deemed a theory of everything, as opposed to a grand unified field theory, which would include weak forces and strong forces. So we're just looking at gravity and electromagnetism here. So if we go back to our surface tension pressure, we can see on the left here in this graph, we have, if there's a molecule in the bulk of the liquid, it has sort of, it's being pulled equally in all directions by its neighboring molecules, but those molecules on the surface have an asymmetric surrounding. So there's a force acting on them, which which causes the area to be minimized, the surface area. And that can be described in this equation, where sigma is the surface tension, L is the length, let's say, of the container at the bottom here. And yeah, and it needs to be divided by 2 because there are 2 surfaces. So if we take that equation and so the how would you say, not the implications, but we're kind of using this model as if the surface area is the surface of the hypersphere, so the surface of the liquid here is the surface of the hypersphere, and we say that surface tension is gravity, then we can rearrange this equation to get F equals G, which is the surface tension, times twice the length. And the length of a sphere is the circumference in this equation. So for G, we use the parsec version of Newton's gravitational constant. For the circumference, we've already determined the sizes of the circumference, radius, diameter, obviously, surface area and volume in previous papers and preprints, and presentations. So I'm just using these values here and putting them in again. They're in parsecs, and we get the result of this is the total force on the surface of the hypersphere, which is equal to 1.15 times 10 to the 31. And the units are meters to the 5th per kilogram second squared. So I'm not sure what the physical interpretation of this is. There is no actual, it's not listed, but what in terms of the Ohm hypothesis, it would be a universal gravitational force constant. And in this context, the word universal is being invoked because we're talking about the entire universe, rather than it being, sort of uniform or something like that. Oh yeah, so this can also be converted into different units, and that gives, okay, yeah, so you can convert it. It doesn't have to stay in this kind of thing, and we get e to the 41, which is very similar to the relationship between the electric force of a proton and an electron, which is 2.4 times 10 to the 43 times bigger than the gravitational force. So that is something to consider. But then if we're talking about the universal gravitational force is, in a sense, proportional to the circumference area, and we know that the hypersphere expanded from the beginning of the universe up to its current, then we can extrapolate backwards, in effect, to see what the changing universal gravitational force would have been, throughout history during the 24-hour period of the expansion, which is the sort of time limit I'm putting on it. Okay, so yeah, we'll skip that. Let me see here. So another way of looking at it, obviously, it's better to keep the gravitational force constant, because even if we have a bubble of water, the surface tension on that bubble is going to remain constant no matter what size the bubble is, depending on other factors like temperature and impurities in the water, etc. But in general, that is the case. But if we were to consider it the other way around, that the universal gravitational force remains constant and we're changing, therefore the gravity has to change. So this was my initial thinking on the subject. And if we were to plot that over the expansion of the universe, we see that the gravitational force would essentially go to infinity at the very beginning, but that's just because we're at 0 volume size, and then it drops in this kind of way. So the effects of a changing gravitational force would have on the other constants. For example, the Planck temperature is shown here. It would increase in this way. Mass would have an effect on that in this way. And finally, the Planck length would also have been larger in the past and decreased. So there's the values there. But this is obviously a very small change in the Planck length, and I'm not sure if it would have too much effect on the physics of the universe, especially in the early days. But maybe that's debatable. But in a large part, this is all academic, because, as I said, Newton's gravitational constant is constant in this model, so it must be the force, the universal gravitational force on the hypersphere that is changing. So we can look at the relationship between the strength of the electric force versus the gravitational force using surface area pressure. So that's pascals to the third. So we take the cube root of the pressure divided by g to get the relationship, and that gives us 4.09 to 10 to the 37, which is very close to the relationship between the electric force and the gravitational force, which is around 10 to the 36. But if we instead of looking at the surface area, we look at the volume pressure, and that would be pascals to the fourth, obviously. So we need the fourth root in this case, and we also get a number that is very close to 10 to the 36. So that could be indicative of that. And then if we take the cubed root of the volume pressure, we get back at 10 to the 43, which, as I said before, is very similar to the electric force between a proton and an electron. But you know, so it's not exact, but it's they're just interesting relationships. I find it interesting that you can get this from the geometry of the own model. So these graphs kind of show because we know that the electric force and gravity are linked through the pressure on the hyperspheres. It's worthwhile, you know, again, returning to determine what the pressure of the hypersphere is over the expansion rate. So here we have the blue line is the surface area. Then we take the Legendre transform to get the pressure in pascals, which is shown on the right there. So, excuse me. So we have the pressure percentage change, which is depicted in this graph. So as the hypersphere grows, obviously the pressure drops. But this graph shows the percentage change in pressure as the hypersphere grows using this equation here. And so as we know that the change in pressure should affect the electromagnetic force coupling constant alpha, based on the previous slide, which showed a relationship between gravity and electromagnetism, and as well as gravity and the pressure on the sphere. So electromagnetic force coupling differentials. So because we have the changing, we have the pressure percentage change, we know that this is linked to the electric force via the gravitational force, if you like, is going to be, let me see. So these are the values that they start from, and these are this is the last value, obviously, which is alpha. So this is how the electric force coupling would have changed as the universe expanded. however, if we have even a 5% change in alpha, it would render stellar fusion of carbon impossible. And we have a much greater, I mean, I think 5% is around here. So it's obviously a lot greater, because all the way to 100% effectively. So there's, I think the implication here could be that there is no matter in the early universe, that the expansion and rotation of the hypersphere happened just purely with space, and then matter was added in afterwards. So what might that look like? Well, I have a video here which uses, again, is this using a Marangoni effect. And it's a very interesting video, but I think that's the idea. The experiments conducted here could be used to model how matter could have been added to the hypersphere and how it would evolve over time. So we'll watch a bit of this. There's sort of people involved in this work. Let's skip ahead. Wait a second, can you hear that? Or do I need to add well, I don't think
there seems to be some echo. There seems to be some echo.
Can you, when I'm talking, is there an echo?
No. When you play the video.
Oh, okay. Well, okay, we'll just we'll live with that. Sorry. So yeah, it's really that effect that I'm thinking of. So the matter could have been added in like one lump, like kind of like the singularity idea, and then it spreads out into galaxies like this. Although from the perspective of the Ohm hypothesis, and much like what Andreas Gimsa was talking about, that as you get like, let's say Earth is here, as you get further away from the Earth, mass decreases in the universe, and that is the same on the hypersphere, because as you go further up to the projective point, matter particles and galaxies and such have to get smaller in order for the projection to remain the same on the tangent space. But that would imply, like, if this is the center of the outer hypersphere, and then the Earth would be in every direction, in an infinite direction away from this. So that would mean that the smaller galaxies are closer to us. So that doesn't make sense. So this would have to, in some way, the physics that are involved in the creation of this pattern here would have to be inverted in order for it to make sense in the Ohm model, which is plausible, I guess. Okay, we seem to be skipping through the video, which is fine. But they're nice patterns, I think you'll agree. It's nice research. I'm not sure how to move. Oh, there we go. So another sort of physical, how would you say, physical property that we can look at is in terms of fluids and surface tension is something called the grand potential. So we have here the surface area of the hypersphere times the gravitational, or the surface tension, equals the grand potential. So we use again the units of measurement for the surface area, this time in terms of light years, times Newton's gravitational constant, and we get this number for the grand potential, which is 1.21 10 to the 17th power. So some other, I mean, we can kind of play around with that and then divide the gravitational potential by the circumference times g, and that gives this value here, which is 651, 0.4. And so I just included that because I thought it was interesting. I'm kind of wondering about the significance of that number, especially since we looked at the norm of the Weyl vector before, and it shows that it has 26. It's a 26-dimensional vector, and so the first one is 0, obviously, and the last one, the norm 2 version, I mean, it has this value, but the 13th, which is the mid value, has 650. So I don't know if there's a relationship there. It's just a pattern I noticed. So we'll move on to universe structure. And really the question we're asking here is the hypersphere a bubble or is it a droplet? And so as we know with bubbles, they have 2 sides, whereas a droplet only has 1 side. So so we're kind of returning to this issue similar to Bartholin and Barber's work, those 2 French physicists who were looking at bubbles. And they seem to suggest that the 3D space is the surface of like a lake. So obviously in that case, they're thinking of it as having only 1 side to the surface, only 1 surface. Whereas if the hypersphere is a bubble, then it has 2 sides, obviously. So, excuse me. These are the pressure equations for a bubble and a droplet, and I got this from hyperphysics.phi. So as you can see, the equation for bubble pressure, for a bubble needs 4 times the surface tension divided by the radius, whereas for a droplet it is only 2 times the surface tension divided by the radius. So if we look at water bubble pressure, which is interesting perhaps, we do the equation. So the surface tension for water is 72 of these units, newtons per meter, I guess, and the exact extra pressure. So we can look here with the bubble diameter of 1,000 mu meters. We have micrometers. We get 228 pascals, which is interesting because it's kind of harmonic with the number we get for the diameter of the hypersphere, which is 28.8 megaparsecs. So we have this kind of harmonic between the 2 descriptions, and this obviously results from some sort of harmonic between the surface tension of water and the scaling factor, which we mentioned in previous presentations was 70. So we can also look at the Young-Laplace equation, and this gives us so we take the surface tension of water, and we're multiplying it by 1 over the radius plus 1 over the radius, essentially. So again, and we know the radius of the hypersphere is 14.4 megaparsecs, which again is harmonic with the pressure of this resulting from this Young-Laplace equation to do with water droplets. And since we're talking about water a lot and gravity and surface tension, it seems to suggest that these harmonics are saying that indeed the universe is a bubble rather than a droplet. So that's kind of, but there's also other reasons to think that based on our previous research that I just showed you in previous slides to do with bubble pressure and the relationship between that and gravity and electromagnetism, etc. We can also look at a bubble pressure differential. So which is this equation actually. So we because we're minusing the interior pressure with the exterior pressure. So we have 4T, the tension divided by OR. So OR will be 14.4 megaparsecs. The surface tension is G. Again, which is just Newton's gravitational constant in terms of megaparsecs. And we get this kind of, as the universe expands, we get this trend here, and these are the values. And we notice that these values are they're in the Planck constant range. So I think that's interesting. And since we've determined that the universe could in fact be a bubble, the hypersphere, I mean, then we know that there is still like an interior inside the bubble. It's not like a vacuum. It's not like nothing exists in there, because there is a pressure, obviously, between if we're taking a differential between the pressure of the inside and the outside pressure, there has to be something there. So we can model this. In a previous talk, I looked at how the hypersphere scaling factor was related to the Riemann-Zeta function via a group of elliptic curves. So we find when we use the scaling factor and map it onto the Riemann-Zeta function, the projective point lies at 0, 140i with a z value of 1, so that's there. And the good thing about this is that we can use the Riemann-Zeta function to potentially provide information about what might lie inside the sphere as well as outside of it and beneath it, which looks like a lot of chaos, I suppose. But not really. It's just sort of analytically continuated from the order here. So we could even think like maybe chaos and order are related through this sort of analytic continuation. So now we get into the main point, really, I think, of the entire presentation, which is the Marangoni Cosmological Catastrophe, subtitled "How the Universe Will End." So the basis of the thinking here is that, well, I'll just introduce the idea of the Marangoni Flow effect to begin with. Essentially, it is a mass transfer along the interface between two phases. So if we look at this experiment here on the right, we see the scientist takes a small drop of, let's say, some kind of chemical surfactant, like washing up liquid, and drops it into a petri dish of water that's covered in ground peppercorns. So, and the effect is fairly instantaneous. As the surfactant bubble surface expands, the remaining water tries to maintain its cohesion by moving away, and then this mass transfer causes all of the peppercorns to move. So in using this then as an analogy for what's going on or what could occur at the end of the universe, we would imagine, as I mentioned before, that water is likened to, or the surface tension of water is likened to the gravitational force of ordinary space, that being Newton's gravitational constant. Whereas the surfactant space is likened to the surface tension of the washing up liquid in this case. And then the peppercorns would be all the stars and galaxies in the outer sphere of the hypersphere. So obviously, if we were to apply this effect to the universe, then we could imagine that at some point, a small amount of this new kind of space with this new gravitational constant is added into our universe, causing this rapid transfer. So we can ask, well, we can use this equation here to determine the speed of this mass transfer. So this was developed by Roché et al. And the results can be seen in this graph here. So we obviously see a very rapid increase of speed, and then it gets much slower and eventually just peters out and stops. So in this equation, this has kind of been slightly altered to include the gravitational constant for ordinary space, which is just g, and then the new lower surfactant surfactant gravitational constant for surfactant space. Then we have the mu, which is the vacuum permittivity, rho, the mass density of space, which in this case has to be 10 to the 113 because that is the 0-point energy value, and it's the only one that works. So the cosmological constant value, which I think is 10 to the 19, just doesn't produce correct results at all. So, oh yeah, and or is the radius of the expanding G space. So the fact that the 0-point energy value is more important in this case than the cosmological constant value could suggest a solution, if this is correct, to the cosmological constant problem, suggesting that it is the 0-point energy value that is the correct one, which kind of makes sense because the Ohm hypothesis is sort of done away with an expanding universe anyway. So the cosmological constant and things like dark energy just aren't really needed anymore. So it makes sense that they wouldn't produce the correct answers. Okay, so yeah, I'll move on. So here I speak about the volume fraction of the surfactant space required is obviously something very small. It's like 1.3 to 10 to the 397 megaparsecs cubed, which is that's in relation to the size of the universe, though. So it makes sense why it would be such a small number. But the maximum radius of our hypersphere, as determined by our previous work on a support vector machine analysis, says that the circumference is around 45.2 megaparsecs squared. So the amount that our surfactant space bubble can expand has to be less than half of that. And based on the previous equation with the speed, we see that there's a, so if we go, there's a certain amount left over, which is 4.09 megaparsecs. So this, in order for this to be made up, there has to be a further rotation of the hypersphere, which kind of makes sense because we spoke of like an expansion at the beginning of the universe and a rotation, which could still be in effect. The rotation would have had to happen some point after the material was introduced, which is also a Marangoni Flow effect. And then we see the Marangoni Flow effect at the end of the universe as well. So there's a kind of a balance in all of this, which I find interesting. So then we can determine the speed at which the rotation occurs, just through simple mathematical calculation. And from that, we can figure out the time it would take for the universe to end once this surfactant space is introduced. And according to that, it should be no less than 2 hours, 10 minutes, and 13 seconds, which is very, very fast, because ordinarily any, oh, well, maybe with the exception of, the false vacuum, but even that would be relatively slow compared to this. So yeah, if we think in the experiment where we saw the scientists drop some washing up liquid into a dish of water with peppercorns ground upon it, many of the kinds of experiments that you'll see done relating to that Marangoni flow effect will also have some oil introduced, which will bind to the peppercorns, and that is just something that they do. So we can imagine that there is a third kind of space in space. So once the surfactant is introduced, you have ordinary space, surfactant space, and then this third space, as David Lynch would talk about. But yeah, so and I'm proposing that the third type of space is likened to oil. So so then we could say that and that is present in our universe at present, and is also obviously binding around matter, so around galaxies. You know, we could obviously attribute this to dark matter, it seems. So then we'd be looking at dark matter, instead of it being, you know, what we know about dark matter, it doesn't interact with ordinary matter, but it is affected by gravity, which means it sort of interacts with space. So that a motivation, we could ask, what is a physical property that interacts with gravity but not matter? And we come up with the obvious conclusion of space. Space does that. So dark matter could be a kind of space, perhaps. So if the surface tension of water is around 72 newtons, and at this particular temperature, and the surface tension of oil is around half that, so around 36, it's the sigma as a median value. That's over a sample of different types of oils, such as coconut oil and mustard oil, etc. And that would mean that the gravitational constant should be right. So the gravitational constant of dark space would be, it works out to this value, around 3.07 10 to the 11 newtons. So surface tension, yeah, and then the surface tension of the surfactant space would be around half that again, so 15, which means that would come out at 1.6 10 to the 11 for that. And I included a picture of dark matter here, just so you know what I'm talking about. Now we'll move on to gravity anomalies from the anamorphic universe model perspective. And one of them this is the last thing. So one of the things I was looking at was the alias effect. So if we know that the projective point from the point of view of the 3D tangent space is in every direction in space at an infinite distance from where we are, no matter which direction we point, that's where it is, then the lines of the gravito-tortio magnetic monopoles, in effect, that are sort of streaming in towards us from every direction. Let's say if we look towards the sun, there's a load of them streaming in to create the sun, to project it where it is, and then through the sun to project where we are. So it has this, it's kind of like a holographic projection. It can project through itself effectively. Then if we have the moon coming in and blocking it, then the moon, these torsion lines have to go through both the sun and the moon. So I'm suggesting this might be a possible explanation for the alias effect, which was discovered by Maurice Alias. And he conducted 2 experiments during the solar eclipse of June 30th, 1954 and October 2nd, 1959, using Foucault pendulum. And so the results concern the anomalous precession of the plane of oscillation of the Foucault pendulum. So he noticed that it began to oscillate more wildly during the eclipse. So it would be interesting to do some calculations to see if we could prove his results through the magnetic monopole proposal, but that might not be doable because, well, I've kind of looked at some of this data, and it does look good, but there's been criticisms, and well, also several experiments have been redone, and some of them have shown an effect and some of them haven't. So there's kind of doubt over the entire thing. But in one of his papers, he actually mentions, lists a number of other gravity abnormalities and anomalies, including some to do with tide theory, motions atop of the Eiffel Tower, which should give you some indication of when he paper, I guess. Size deviations of the to the south noted on falling objects, variations in amplitudes of the deviations to the east noted on falling objects, and abnormalities in the action of terrestrial rotation on the flow of fluids. So that's pretty much written verbatim from his paper, 1959. Then we also have other gravity abnormalities or anomalies. One that John Hodge looked at, the Pioneer anomaly. And I believe the Pioneer anomaly is explained, you know, in the textbooks, let's say, or the literature, something to do with radiation. One side is getting radiation from the sun, the other side isn't, so there's a slowdown. And John, his proposal was that they should be measuring the slowdown from the sun rather than from the Earth, I think was his proposal, which is an interesting idea, and, you know, the kind of thing that people might overlook, sort of a simple explanation like that. So just quickly, the conclusions are there may be a universal gravitational force acting on the surface of the hypersphere. The force is not a constant in terms of the expansion of the universe. The universe did not have any matter in it when it was created. It was added in later. The universe structure is like that of a bubble rather than a droplet. And the end of the universe will take 2 hours, 10 minutes, and 13 seconds at the least. So, and finally, dark matter could be a kind of dark space. And those are the references. And that's the end of the presentation. Thank you. But that wasn't too insane.
Yeah, you have a lot of stuff there. That's good.
Yeah. I mean,
that's good.
I don't know. That's kind of my style of presenting. Like I know normally you take one subject and maybe focus on that and really go in depth. But yeah, there is. I just found it better to I feel like this is all one subject in a sense anyway, because it's to do with fluids and gravity. So, but yeah, maybe I don't know how long that was. It was about an hour. So as I expected it would be. So thanks for sticking with us. And,
so, Rajan, do you want Gad? Do you want to speak first, or
yeah?
Should...
Yeah, just a couple of clarification questions or points. One of them is that you said that gravity, you know, there is a distance. I mean, it increases, then it decreases. You know, when you go to interior.
Yeah.
So it may be due to formation of vacuum. My feeling is that all the vectors are, you know, canceling each other. So at the center, I was thinking even before about the black hole. The inside of the black hole may be vacuum, absolute vacuum kind of.
Okay.
So that's pulling the thing inside.
Yeah.
And it's because of the vectors are canceling, like you showed. And then, you know, I do from the time. I have the new paper with OJPS that you may have seen that, right? We discussed a little bit last time. So that is, you know, that's very revealing about time itself. I think we have to know the vector and the scalar. So that's the other aspect. And then I may have some other things, but I will end with the dark matter, about the dark matter dark space. The thing is that if it is like Emmanuel and myself and Roger, we're talking about superluminal thing, if anything goes faster than speed of light, you cannot see it. You know, it's a very simple. I mean, you can actually go into details why it is so. So then it appears dark. So your dark space may be superluminal phase.
Right. Yeah. So I suppose when they talk about dark matter, the reason why it's dark is because it's not interacting with ordinary matter.
Yeah.
So,
WIMP. They call it weakly interactive massive particle. I mean,
WIMPs. That was another theory, wasn't it, back in the 90s? But I think that's been disproven now. But
I'm also exactly on the same opinion with Christopher. That first I want to congratulate Christopher for your excellent presentation. The slideshow was wonderful, and you put a lot of work of that, and this is worth continuing. You took that's the correct way for physicists, not to start from the maths, but actually from phenomena, from observations. This is observational physics. That's the correct way for me, in my opinion, to do physics. Because, you know, many people, they're just mathematical physicists, and they originate from the maths. No. You have to do actual physical observations, make analogy, And don't be discouraged about people saying that quantum mechanics is different from classical. No, it's not. For me, classical mechanics is the synonym with logical mechanics. Or quantum mechanics is just ignorance. That's all I believe it is. So there is now no distinction actually between classical and quantum mechanics. The mechanics just one. It's all the same. The quantum, all this widness is not because we don't understand things. That's all. Yeah.
Oh yes,
I'm not saying that it's not that it's deterministic or random. Random, it's okay. It's even in the classical physics, you have randomness. Yes. Okay. Yes, it's okay. Again, classical mechanics is not the same definition as random you have in quantum. In classical mechanics, if you say random, you mean it's stochastic, deterministic. But who knows what exactly if it is also not the case for the quantum physics.
Yeah, exactly.
Because we stop at the level of the standard model particles. We don't know if the vacuum itself has particles. We say no, it's actually not, but we don't. It's not sure. So if we go to the Planck scale or even sub-Planck, maybe there are particles there, and then you cannot say it's random. You don't know that if you don't include the new particles. So I congratulate you from the whole thinking you did and starting making analogies. Yes, that's exactly. I actually also believe that this is related. The quantum entanglement you have started is related with some kind of gravitational tension and torsion. So you imagine that everything is connected with some kind of ropes.
Essentially.
In that case, the propagation of the torsion effect will be much faster than the speed of light.
Yes.
Than transverse waves. So tension and torsion will be propagated much faster. So because they say quantum entanglement is a non-local effect, and the term non-local effect means that it has no signaling in it. There's no information transfer. But in my opinion, there must be some kind of signaling. It doesn't make any sense. I don't know. I mean,
I find it very difficult to talk about it without mentioning like some sort of data transfer
of information. Yeah, know, they say that it's the two components which are quantum entanglement are actually a single, but that's only words. Well, what does it mean? What do you mean it's single? Action must be transferred. It's not popping out from one point to the other. There must be some kind of interaction. Yes. So yes. Also, the other I'm 100% with you is that dark matter is not WIMPs.
Right.
I mean, they tried now over 30 years and they couldn't find anything.
Yes, it's true.
It has something. It has something to do definitely with the vacuum.
Right.
So if you have a normal baryonic matter like a galaxy, and you start the galaxy turning, it polarizes the vacuum around it.
Okay.
It makes some kind of you imagine you have a cobstacle inside oil, and you turn the oil, but then this affects also the pressure on the oil. It can add to that. It can slow it down, but it can also make it rotate faster because you add it into the mass of the So I believe that
it could be something vacuum, there, right?
Yes, vacuum is actually gravitational, but because it's uniform everywhere.
Yeah.
Actually, I believe vacuum is the source of the origin of gravity. So you have water, you have the oil, the soap you described, and then you put condensed matter inside. But imagine this condensed matter.
Yeah.
It's not vacuum. Where you have condensed matter, there's no vacuum. Yeah, even if it's 99% of the atom is, they say it's vacuum, it's not exactly that because
I agree. Yeah.
So if ordinary matter represents holes, then you have a gradient in the vacuum. The whole vacuum then, the whole homogeneous surrounding vacuum is pressing to the hole. That's gravity. That's good gravity effect. So where you have ordinary matter, you have actually a lack of vacuum energy.
Yes.
So you have the water pressing in the hole inside. Imagine suddenly there's a bubble, an air
Right.
bubble
Yeah.
inside
Yeah.
the
Yeah.
water, and then the whole vacuum is pressing into this bubble. That will create something
Yeah.
similar to gravity, to negative pressure, something. I mean, yeah.
So that would be like on a very small scale. Are you talking about with particles that there's like a lack of something, and then that creates this pressure?
Yeah, because if you're inside a homogeneous atmosphere, you cannot feel the pressure. It's inside you, it's outside of you. But if you have an anamorphic, localized anamorphy, which is there's a gradient in the pressure, then you can feel it. So the pressure is wherever there's an inhomogeneity in the vacuum energy.
Yes.
You have a gradient, something anomalous. But
and it kind of links in. I think I'm coming at it from a slightly different point of view, and I'm not sure if I'm correct or anything. I'm definitely going to have to revise some of these ideas. But so this idea that like matter could be, I know, like I think if you're talking about like on a quantum level, maybe it's like a hole which creates some sort of differential, and then the combined effect of all of those differentials form to create matter or something. That is interesting. And that's like a completely different idea, sort of train of thought, which is cool.
I was actually my eyes popped out when I saw the Marangoni effect, because I didn't. I think I have seen this before somewhere, but I didn't knew that it had a name. There was an actual person who discovered this, named this effect, and studied this effect.
Yeah.
So this is very good, yes, because I also believe that first it was only the space expanded, only the vacuum expanded from something. If we assume that Big Bang is correct, so in the observable universe, you don't have initially matter. You had this vacuum energy which expanded rapidly within an attosecond, fractal of a picosecond or so, and then a phase transition occurred, and you had this this initial plump of plasma of very hot energy. But then you come in with your interpretation, and it's very interesting, because then you see that immediately the small lumps are expanding exponentially fast, and this can also then contribute to the formation of the galaxies, and how now because they have a problem in with the latest observations with a telescope, the Webb telescope. Yeah, they find galaxies which are they cannot they are very much well formed.
Yes.
They cannot explain why they are so fast formed. They shouldn't have been so
large,
very formed galaxies so far away.
Yeah.
They should be primitive state, but they find galaxies which are nearly as our galaxy, formed, well formed. They cannot explain it. But your effect, this Marangoni effect, you see a uniformity of all the blobs spreading out, and that could explain all the galaxies more or less they have the same age.
Yeah.
So is this Marangoni effect? Is the Marangoni effect when that happens? Is it done at superluminal speed? Are they all the blobs? Because you know the Big Bang, the inflation is a superluminal event. You know that.
Of course.
Mainstream, because if you have this enormous, in a fraction of a second, covering light speed, this is a superluminal effect.
Without a doubt, and it's alive because we're dealing with space, expanding as well.
Space can overcome the speed of
the matter is being transferred, or how do you say, transported across the interface, which is space.
Exactly. But your thing is very correct. If we accept that Einstein is correct, the theory, the maximum speed is c, then matter cannot expand faster than c.
Right.
But if initially in the Big Bang only space inflated, and then a phase transition started, then that's the proper explanation. But the Marangoni effect cannot be superluminal because we are talking now about mass.
Yeah.
So but this explains why all the galaxies are uniform. That's a very good explanation.
Yeah. So
the only problem I want to ask you, you said in some instance, referring to the Marangoni effect, you said something. There's a slight problem with this theory. Because the Marangoni, when it's done in an experiment, you see that the larger blobs going to the perimeter and the smaller blobs staying in the center. Is that right? Did you say that?
Yeah. So in the video that we saw, it was the larger blobs closer to the center and the smaller ones at the outside.
Okay. So the larger blobs staying in closer to the center, and the smaller are expanding. Yes, but I don't know if this is what is observed now. That the larger galaxies are because there is no center. There's no center. Yes.
Yeah. I tried to address that in the talk, but it was a little bit difficult.
You believe that the Earth is the center of our solar system is the center of the Big Bang.
It's at the south pole of the hypersphere.
Yes.
So
yes.
Technically, it's not even. It's both on the tangent plane and the hypersphere at the same time. But and then so as you go out from that, you have all the galaxies and stars on the hypersphere, and they have to get smaller and smaller as they go up to the projected point, so that when they're radiated back down, they maintain the same size on the tangent space. So I'm thinking that if we drop the oil onto the sphere, let's say, and the bigger ones are at the bottom and the smaller one, you'd be dropping it at the top, you see, and it would expand out the other way, I think. See, this is all kind of new, so I need to make sure I'm saying it right. But it seems to me that the smaller ones then would be closer to us, which would, and then they'd be smaller when projected, and the other ones would be even larger when projected out. So our entire universe would just look really weird. We'd have these really big stars far away, and
I believe, Christopher, that with the Marangoni effect, you are really on something.
Right.
You're really, I mean, this is a PhD material. You should definitely continue on this line. Yes, I like that very much. Actually, my eyes popped out. I couldn't believe that because this explains a lot of things. The Marangoni effect.
I really like it.
And this also proves that vacuum is actually a medium. It's material. Vacuum is material for exotic properties. And I believe also Rajan agrees with me that the vacuum is not nothing. It's actually a material.
It's actually a balance between the superluminar and the subluminar. Vacuum is in between.
Yes.
It's trying to balance between the two. So that's why the particles can pop out and pop out.
Yeah. I like that idea. Actually, you could have something similar with like particles maybe traversing through the hypersphere and that they just pop in and out. It could be another thing. So it's interesting. Yes. You made a couple of points that I'm not sure if I addressed it properly, because the mass transfer of the Marangoni effect when you drop the oil in and it spreads out to create the galaxies, that might be. I mean, it's the same effect as the other, as dropping the surfactant droplet onto the petri dish. In that case, you have like these little grains of pepper, and they move out. So they're not actually moving though, because it's like the water that's transporting them, which is space. So it's allowed for them to move faster than the speed of light. But on the other side,
yes, that's a good explanation. Yes, if space is carrying them, then no problem, because space can expand superluminal. And it's the carrier of mass. The mass itself is not propagating. Faster than light. But if space is the horse which is carrying the jockey, which is the mass, there's no problem. Yeah, that's a good explanation. Yeah.
Cool. So I'm hoping that the same will hold true for the other, with the alcohol droplet falling and that effect.
The analogy is very good. Yes.
Right. So if that holds, then fine. And then there's the other issue that, like, let's say we have all of the matter on the bottom of the hypersphere, or wait, let me think. Let's say it is on the bottom, just for argument's sake, and then we rotate the hypersphere, and we can continue to project that. It's going to, I think I showed it in a previous presentation. You would have like a lot of matter all contained in one area. So it would appear, it would be projected into one area. And then when we rotate, it's going to rotate and expand out and fill the entire universe with all the galaxies all around us, and then stop.
Like oil tension, which covers a surface. If you have imagine a sphere, and you drop from the top, from the north pole of the sphere, some oil, it will, because the tension, it will cover the whole sphere. I mean, the surface tension.
Eventually, yes. But I think the point is
substrate for that. If you want to do that, you need a substrate. In your case, what is the substrate? In order to have surface tension, if you drop the oil, you need a surface to conduct with the oil. So in your theory, what is the substrate?
Well,
if your oil is vacuum is the water, But what is if you have, in order to have tension, you mean tension between the water, inside the water, without the substrate?
What is what do you mean by a substrate? Sorry.
So you mentioned a hypersphere, yes?
Yes.
This hypersphere is the surface is water. It's a vacuum. I mean.
Yeah, I think so. Like, this is kind of what I'm getting at. If it's a bubble.
Yes, assume the surface of the bubble is the vacuum.
Yeah.
It's some kind of unknown material. So you don't need a substrate. It's just the bubble in the void.
Yeah.
Yes.
Yeah.
Okay.
This is what I get, I guess.
You mentioned the example with the oil dropping it on a hypersphere and how it expands with the Marangoni effect. But the Marangoni effect, yes, it's okay. It's Marangoni. The pepper is the pepper grain is the matter, ordinary matter, and the oil is vacuum. Yes.
Well, could be dark matter, dark space, but I'm willing, like that, I'm willing to bend on that topic, but I think the other side with the surfactant and that ordinary space is likened to water and the surfactant space, like, again, it's not that it has to be this way, but I'm just saying that's the argument. If I say that that's not true, then I don't have anything. So I'm not going to do that.
Christopher, I want to ask you something. If Rajan doesn't, because I don't want to monopolize the conversation.
Sure.
Rajan, are you okay?
Yeah.
So I want you to explain me, if you can. You said something in one of your slides, and also I could suggest you. The slides were perfect, but just put a number on the slides. So the other can refer very easily. Just show me slide number 3 again, number 46. I don't know. So just put if the slides have some numbering.
Some numbers.
So
that's a good point. I'm actually amazed that they don't just automatically put a number in there, because I mean numbers are very.
I couldn't see any number. No, I couldn't see a number on the slides.
Yeah.
Slide number 1, slide number 2. But I remember what I want to ask. So you in your calculation, which I believe are also correct, you calculated the vacuum energy, which is very close to the predicted. It's actually the predicted. It's 130 over 10, which is enormous energy. It's a joules per cubic meter thing. It's a very enormous energy.
Yeah.
And this actually is the problem, the cosmological problem.
Yes.
Why the vacuum energy is predicted by quantum theory is so big, and we don't see anything of that. We just see instead this ridiculous small 0-point energy, which is minus 9 over 10 joules. So compared to 110, it's almost 120 degrees, 120 more than 120 orders of magnitude larger. They're predicted from what we actually observe.
the worst prediction in science.
Yes, exactly. Cosmological problem. Yeah. The cosmological constant problem. Yes.
That's it.
So how you explain this?
So
According to your theory.
yeah, so that's interesting. So my
I
understanding
mean,
was that
we should be all dead by now. With that kind of energy, we should be all dead by now.
okay. Well, I'm actually going to admit my ignorance on this one then, because I didn't realize that was the case. I thought that the 0 point energy could exist at that level, and that it wasn't a problem. Oh, okay. I might have to rethink that part. Thanks. That's good to know.
No, I give you my explanation.
Yeah, please do, yeah.
So it's actually, you cannot the quantum foam, it's called, with all these pairs popping in and out, and virtual particles, they call it. Yeah, it's like water boiling, and you spread some vapor out. Yeah, so they cannot direct measure that, but they extrapolate that, and not I mean, they deduce that, they calculate that from the expansion of the universe, from the Hubble constant.
Okay.
So you can actually look for the calculation from the Hubble constant, from the expansion of the universe. Then you can calculate the 0 point energy. From the,
right. But what I'm asking you, so like I would have thought that basically, based on my current sort of and past reading of science, that the 0 point energy and 0 point energy figure were sort of accepted or in some way plausible.
Yes,
yeah.
Actually, what is the mainstream opinion is that the expansion of the universe is caused by the 0 point vacuum energy, because that's now the funny thing.
Yes.
The 0 point vacuum energy is actually with time increasing. But because the universe is expanding in an analogy way, then this will keep the same density of the 0 per cubic meter. So so from somewhere, from nothing, well, we don't know from where. I mean, I believe I have a good idea from where. Okay. There's some kind of energy coming inside our Cartesian space. So the vacuum energy as a total is increasing with time, the vacuum energy. But the density per cubic meter is the same.
Right.
Because you have it's expanding, so you create even more Cartesian space, which is filled with more of this 0 point vacuum energy, and then it remains.
The thing that I'm confused about is, I thought you said we'd all be dead if the energy was that high.
Yeah. So, wait. Now, here comes the important part. Yeah. So the 0 point vacuum energy is small. The predicted, however, from the quantum from QAD, from quantum dynamics, is this enormous energy. So where's the rest going? Where all this 100 degrees difference of magnitude? Where isn't it hidden somewhere?
Right.
Or is it some kind of energy we cannot perceive? We cannot not just perceive. It has no effect on us.
Yeah.
It's dark. So what it means dark? Dark does not mean that there is no matter and energy there.
No.
It means that it has no effect on us.
Yes.
Yes. So you don't feel any pressure. You don't feel any heat, and you don't get affected of that, even if it's 300 orders of magnitude as a value. It cannot affect you. It's similar to what they say about dark matter, that it doesn't interact electromagnetically, but only gravitationally. So you have this kind of energy that interacts not electromagnetically. It may, I believe, it interacts gravitationally, but we don't feel it because it's homogeneous. So this means only that it's a different type, a different phase of matter or energy. It's an exotic form of energy we didn't discover yet.
Yeah.
And what kind of energy can be that is not the known, one of the knowns? So for me, there are two categories. you have luminal energy,
Right.
and you can have something which is not luminal energy. I mean, luminal energy is the boundary. It's the highest speed you can have
Okay.
so in our space-time, the highest speed you can have is the speed of the photon. Yes?
Yes.
The speed of light.
Yeah.
And this defines our space-time, as Einstein very correctly put it.
Yes.
Einstein made special relativity all around the speed of light. It's only absolute value he used in his theory, yeah?
Yeah.
So the speed of light is our boundary for our space-time, but that doesn't necessarily mean that there are no other space-times existing.
Right.
Where the boundary, there is a particle, but it has no boundary at C, but it has a higher boundary, so it's superluminal.
Oh, well, this is interesting when we apply it back to the Ohm hypothesis, because we have the hypersphere, which is the universe, and the tangent space, which is also the universe. One is flat, one is curved.
Yes.
But then we have the interior of the bubble, and we have the exterior of the bubble. So we have this like other space. And then throughout that other space, we have these lines, the electromagnetic lines of instant superluminal transmission. So perhaps
the monopoles. You're talking about the monopoles, yes.
Yes, and that kind of links back to Rajan and what he's been talking about for years, and yourself, and these three different areas of superluminal, luminal, and then subluminal, which is the matter.
Subluminal is matter. Subluminal is matter.
And these magnetic monopoles then kind of pierce through all three, if you like, or are all three at the same time.
So yes.
Three is the one.
Yes. In my research, what I did, because I actually started from observational physics, and I'm still doing observational physics. I'm using only math later on. And actually, GET was unit analysis is a very good method. You can extrapolate a novel equation just by considering the units, meters.
Only one portion.
The general equation from your units. This is called units analysis. It's very important. But this is
but only
later on. I use that later on. I'm doing observational physics. Yes.
Yeah.
Yes. So in my theory, the vacuum is the third player. Sorry.
No problem.
Ναι. Έχω μια σύσκεψη. Μπορείς να πάρεις λίγο. Yeah. So in my theory, Christopher and Roger, you have three things. You have the things you can see, and the things you can two things. The things you can see and the things you cannot see.
Yeah.
You cannot observe or perceive. So you have matter, you have light. So these are the first two players. And then you have the third player. You call it vacuum, but you perceive it as nothing.
Yes.
Doesn't make any sense. Doesn't make any sense. If you believe that if you believe in physics that there's no such thing like nothing, the vacuum cannot be nothing. It must be some kind of energy we don't know of, and we just see its evaporation. It's the 0 point energy is nothing. It's just evaporating. A very small component. Some kind there must be this. If we accept that the vacuum, what I say is superluminal energy, and that's why we cannot perceive it, and we see it's like empty, but it's not empty. It's full actually, but the energy we cannot see. So we perceive it as empty. We observe it as, but there's also this small evaporating energy, like a black hole, like with the Hawking's radiation. There's a small energy a black hole radiates. So what we perceive as 0 point vacuum energy is actually the evaporation of the superluminal energy, the dark energy, the hidden energy. So the matter and light and the vacuum are all interlinked. We are all in superposition. Even inside an atom, you have 99.9% there is vacuum. Yes, that's what we say. So it's not like you could say mathematically it's a projection, but physically, I believe it's all together. We're inside, but we are not in the same space time. Spatially we are all inside the vacuum, but the vacuum itself is in another space-time, in another time dimension. Because it's superluminar, you cannot have the same space-time with normal matter and light. So normal matter and light and vacuum are in superposition with each other, but are not but are not in the same phase. So vacuum energy is out of the, I mean, the big energy, the 113/10, that energy, not the zero. This energy is out of phase of our reality, of our luminal energy. Luminal energy is light on all the normal matter, but which is subluminal. I mean, the speed of light is the boundary. So what you see as 0-point vacuum energy, which is responsible for the expansion of the universe, is actually evaporation product of the superluminal energy, which is the main component of the vacuum.
Right. Yeah, I think it's interesting because you know the picture I had where I used the Riemann zeta function and I have the bubble universe. Yes. So we have energy inside and energy outside, and we may even be able to like use the values of the Riemann zeta function as like maybe values for this superluminal energy that exists outside and permeates through the bubble in some sense, or like you're saying, evaporates into it or out of it. I'm not sure. So I feel like because that's a 4-dimensional space, and we have like we could do dot products. I'd have to look this up again, but you know, it's kind of a distance measurement dot product. And it's only valid in 4D space, I believe. No, sorry, no. I mean, it's valid in any dimensional space. Is what I'm trying to say. Okay. Whereas I think the inner product is only valid in 3 and below, but it doesn't. You can't do 4D with it. So, yeah, I had some notes on that issue. I don't think it's here.
Be careful, Christopher, because there's a trap when you in any research. There's a trap. You have to distinguish between effective models and physical. So effective models are models that are not the actual ones, but are used to explain things. So you have to distinguish in your case what you mean by if your model is what part of your model is physical, and what part of your model is effective just to explain things.
Yes.
You have to make a clear distinction.
Yes. I think this point about the dot products and all that, like I don't want to labor it too much, but effectively it was just a little bit of mathematics, and it was nicely sort of backed up by some other very simple ideas of mathematics to do with Euclidean distance or something. But basically what I kind of learned from it was like there's this huge amount, and I think it was the result was like, and from our perspective, an infinite amount of energy in the 4th dimension. So just outside the sphere, therefore, what's going on outside that sphere is just like, if we were to go out there, we're just obliterated, like, I think.
Okay.
You know?
Okay. So because I imagine that physically the actual one is the whole thing is just like water, a tank of water. I'm not talking about the aquarium, the glass. Just imagine a blob, a bubble of water.
Right.
Yes. And inside this water you have this pepper. You know, the pepper sprouts, the pepper flakes. Yeah. That's how I physically or even ontologically imagine the universe. But now you're talking about, I believe that you physically describe it just like a bubble which has an empty interior inside.
Yes.
So that's our difference with our models physically. Because I don't believe there's
emptiness.
There's empty space. There's just the water is just a bubble, you know, a water bubble. Because the water bubble is imagine a soap. It's a liquid. Which is the surface of the. You can also say that it's the water, and inside is air. So you imagine that the universe is. First, you're talking about the observable or the whole universe. You're talking about the observable universe because they say that the whole universe is 500 times larger than the observable. That's what they say.
Oh, so, yes. The whole universe is the bubble.
Okay. Yeah, that was actually I was thinking that that you was arguing about the whole universe, not just the observable. So you imagine that your universe is a bubble, so a bubble, and we're living inside, all the galaxies are on the surface of the bubble, but at the center, physically, you imagine there's nothing.
No, not nothing. Because so my argument is
hyperspace.
Yes.
Okay. So okay, I understand. But in my case, imagine I imagine again the sphere, but the interior of the sphere is the same as the surface.
Okay, but that means we can travel into it, can we? We can travel straight to it, or we can even look into it, or can we?
Yes, I mean, our universe has volume.
No, but remember that the hypersphere is a four-dimensional sphere, so the surface is three-dimensional.
So now it's effective, but then so the surface is actually volume in that case if you project it.
But we're not even most of the universe that we look at, I'm arguing, is not on the hypersphere. It's on the tangent space, which is also three-dimensional, but it's infinite and it's flat. And so it's only the projection that we see.
This cannot be physical. This is an effective model.
Because possibly, But what's
using geometrical terms now? I'm talking about So I imagine.
Yeah. So this is interesting. I'm not familiar with this debate in or arguments in science or philosophy of science between physical models and effective models. This is new to me, but is there?
Yes, I mean, I believe that the universe is like is a sphere, like the Earth is, because the gravity, if you leave the gravity to act for billions of time, it will create a sphere. That's the nature of gravity.
Yes.
It cannot create a square. Because all the things are coming from all the sides, and eventually the shape you will end up if you leave gravity to act is a sphere. It's nothing else. It cannot be anything else. So if you accept that vacuum is gravitational, it will form a sphere of vacuum. So the whole universe, not just observable, is actually a sphere of vacuum. But it's a ball. It's not empty inside. It's actually full inside. So you can travel from.
That's very different model, though. It's similar in the sense that it's right. You've got a sphere, and there's a sphere over here, but the two are quite different. But I mean,
I got a ball, not just a sphere, a ball. Full.
A ball, yes. So. I don't know. They're just two different models at this point, and it's like, how do you weigh them against each other? Maybe there's some. I think you need a deeper analysis to do that.
How you explain the flatness of space?
Because that's how I can. Well, that's just what I was going to ask you, because I remember Rajan brought it up to me. I was talking about a hypersphere universe, and he was like, "But then that would need to share, wouldn't it?"
The flatness of space is, as I understand correctly, if I understand correctly, is like similar to the Earth. The Earth is a sphere, but when you go close enough, you see everything flat. So the triangles are 180 degrees.
Yeah.
When they measure the distance between galaxies, they get a triangle with 100 degrees angles, the total angle, the number of the angles. So that's this flat space. Yes. So if we imagine that like in your case, your universe is a sphere, you call it hypersphere, and then you project. It's like a map, projecting a map.
Yes.
But the physical thing is actually a sphere, even if you call it hypersphere. It's a sphere.
Yes. Well, no, but it would have to be. It would have to be four-dimensional to project a three-dimensional space. Because we live in a three-dimensional universe, so the sphere has to be four-dimensional in order for it to project down.
I cannot imagine a four-dimensional sphere, but anyway.
So one other.
So I believe actually in your model, it's the same case for the universe. If you imagine the universe is like a big Earth, if you go close enough, because we cannot go, we say only the observable universe is just they say it's 13.8 light years in diameter, in something like that, yeah? 26 or 13.
Billion.
26, yeah. But because it's expanding, it's much bigger and so on, yeah. But this is just a small part of the whole universe we see. Because they say that the universe is, I think the last number I checked was something like power of 500 over 10, something like that, a crazy number. 200 power over 10. So of course we see it flat.
Yes.
We could just,
well, yeah, but isn't there a problem with that argument, though? Because I think it's been raised before a lot that the universe is a hypersphere, so therefore 4 dimensions of space, and it's a sphere. And everyone, like, I think even Gerd has the same kind of model, but he's different things going on in Gerd's model. But then they just say, okay, so the reason why space looks flat is because it's so big. But then you could always, like, you could look further and further and further and always find it's flat, and then you just say, oh well, then the sphere is just bigger than we thought. Well, it's just you can't ever disprove that, I suppose. Not saying that you could disprove my model in the same way or anything, but I think with the Ohm universe, though, the sphere is very much finite. It's only 14.4 megaparsecs in radius. Like finite. So anyway,
case, it's fine. Yeah. I believe also in finite. I don't believe in infinite. I believe also in a finite universe. And I mean by that not just observable.
No, but I'm saying, you know, if we're looking, we're probably, will we ever, do you think, find a curvature of space? I don't think we will. I predict from my model that we will never find a curvature in space because the tangent space is flat, and that is what we are measuring, not the other one.
You're saying, in your theory, the universe is actually flat. It's not a sphere.
No.
The projection, the hypersphere is
curved.
Round, but then the projection is a flat plane.
Yes. And I also predict that the density of matter as we go further out from our position, like as we look further out, will always decrease as we look further out. That's one prediction I make, and the other one is that we will always see increasingly greater redshifts the further we look out, like up to infinite redshifts. There will be no cutoff. I believe the Big Bang model has a particular curve, and that curve ends at 13.8 billion years. Now, they've already, with the James Webb Telescope, discovered a redshift that was higher than, I think the redshift.
There's some anomalies, which are not predicted. 14. Yeah, that's so sure.
So now they found, what am I saying? It couldn't be 12 because there's already redshifts of 16, and maybe it was like 24 or something. But anyway, so whatever, I've forgotten the value, but they've already found redshifts greater. And so now they're like, oh, well, we have to tweak the model, just make it so that it goes back further. So now the universe is a bit older, and now everything has to be tweaked. I predict that it will just never end. You'll always find bigger and bigger redshifts. And so if we do, I mean, that's another one that's kind of hard to say. But at a certain point, you'd have to say, okay, the Big Bang model is wrong. We need a replacement. I think maybe at that point, this is a good option.
Yes. Do you know how they predicted I told you a number, what they estimate is the whole universe. It's 250 orders of magnitude larger than the observable one, if I remember correctly. How do you know how they do the calculations for that? How they calculate that? They take exactly this 30.8 we can observe, 30.8 billion light years we can observe, and they say from this distance the triangle is still a normal triangle, 100 degrees. So from what distance, from what radius and up, it will start deviating from the total of 100 degrees. And then they say from that, they calculate that it must be at least 250 orders of magnitude larger than the observable. That's exactly the thing they do for mathematical calculation.
I don't know.
To make it flat, right? To make it flat.
Not,
my headphones. Well, that's interesting. I might look that up, or if you could send me a link or something to that.
Yes, of course. Yes, the non-observable. It's. I remember last time I checked. It's 250 over 10. It's 250 orders of magnitude, I believe, if I remember correctly, larger than the observable. That's the predicted one. And this is not.
Yeah. I see what you mean. Yeah. I'm understanding you now. Yeah.
Yes.
Okay, that's interesting. I will look into that because
because the observable, the observable is just what light we can see with light. We cannot see farther because now the space is expanding faster. The space with a galaxy on it is expanding faster than the speed of light. So the light we cannot reach anymore. So there's a boundary. We cannot see farther of that.
Yeah.
And actually, the boundary is reducing each year because more and more space is expanding. So now we can see, today we can see 13.8 light years away. In 10 years, in 100 years, will not see 13.8 light years away. We will say, for example, 13.7. Yeah, less, because it's flying away, things flying away from us.
Yeah, but this is the problem I have is that we already found out about the universe expanding, like, was it Lemaitre or, back with Hubble as well. And so they have data from the redshifts all the way back then. Yeah. And it's been expanding for about more than 100 years already. So we should, based on what you're saying and based on what they're saying, I think more importantly, because they're the proponents of this theory to begin with, I think we should be able to see some difference, but I don't think we do. And the points that I want to make there is that in the Ohm anamorphic universe model, there's no expansion of the universe because so let's say you have the sphere, the hypersphere, and it has all the galaxies on it, and then the projective light shines through them and projects them onto the tangent space, and because of the angle of projection, it stretches them out, and that stretching then when the light comes back towards us makes it look like everything is
interesting. I didn't. So in your model, you don't have expansion of the universe.
No, there's no expansion.
A play of light.
Yeah, it's all an illusion.
So the galaxies are just shifting places in the hypersphere, but the whole surface is the same. For the hypersphere does not change size. The galaxies are shifting. Okay, that's interesting.
Yes.
Yeah.
So that's why it's anamorphic, because the shape on the sphere then is projected out like a shadow is anamorphic. It's stretched.
Okay.
Yeah, and then the further away it is, the more it's going to be stretched because of the angle to the tangent plane. And that's why it looks like everything is more stretched.
So you have to clarify more, Christopher. You have to clarify more when you're talking about anamorphic. You should clarify that.
Oh, do you? Right. So
it's more clear, and it's like a general suggestion.
Because I think I have a presentation specifically on this subject about anamorphic universe model. I think it's one that I was meant to announce and I forgot. So it is on the channel. You can watch it, but I think there's a definition. You're right, for anamorphic, and I'm getting a bit mixed up between the terms stereographic and anamorphic. But anyway, there's a well. When I say mixed up, I mean I'm not.
No, I watched your previous. Presentation. Yeah, but it was just you and Rajan, I think.
Yes.
You referring to this? Yes.
Yeah, the one with the quasars. Yes. I explained the time dilation of quasars, and in that particular instance, I used because the quasar is closer to the light source than something. So its shadow then on the tangent plane makes it look bigger, more stretched. So we think then it's redshifted, and then it must be further away, but it's not. It's just closer to the thing. So that's kind of an interesting anamorphic projection aspect.
I now see some similarities with the other theory of holographic space-time.
Yes.
Are you familiar with?
Yeah, exactly. I think I mentioned that about in the introduction to that talk. I talk about similar theories, and one of them was de Sitter space, and the fact that has no It has no singularity for a start. But then de Sitter space is when everything is expanded away and there's like space is just empty
Yes,
and there's nothing left.
yes, de Sitter space is actually invented for the dark energy. So de Sitter space is a space which is filled only with dark energy.
Right.
It's an effective model. It's not. But you could say also the vacuum. The vacuum, if the vacuum, this 113 magnitude orders over 10, if it's all this dark energy, you could say that this is the space-time of this superluminal energy, which is the de Sitter space. The Sitter space. It's a different space-time which is filled only with dark energy. But we are in superposition. Our space-time is in superposition with the de Sitter space because we are surrounded with the vacuum. So,
well, that makes sense actually. But the odd thing about that is that I think, you know, if you have this expansion, and then when we talk about the universe, the holographic model,
yes,
everything is compacted at the boundary. So it's like everything's expanded out, and then it's compacted on a boundary, and then it's projected back in. So it's on a, you know, it just gets a bit weird. For start, it's a compacted boundary. So you're taking space and squashing it to 2D in a mathematical sense or something, and that's fine.
Yes.
And then you reproject it back into 3D space. So they're projecting from 2D into 3D, whereas I'm projecting from 4D onto 3D.
Okay, I see.
So my model's better.
Suskin is a believer. Professor Suskin. Have you seen
Suskin? Yeah. I'm actually really surprised it's Suskin.
Yes.
Yeah, I'm surprised that Susskind and the other physicists I'm talking about didn't already discover this model, because it's considering that it's, you know, they use a stereographic projection so much, and then they're interested in this holographic projection model. You'd think that they would have floated this other one that I'm talking about much earlier. Like I'm talking about.
This is your thesis. This is your thesis. You will taught him. You will taught to the world this new idea. This is your thesis.
I hope. I'd like to. It'd be great, but I don't know. We'll see how it goes.
Discuss it with your advisor, and I believe you are something on. I mean, this Marangoni effect, this Marangoni effect was perfect. I really liked it.
Thank you. Well, the trouble is my advisor is not a physicist like yourselves, so he is. His background is computer science, and he's very much specialized. So if I were to discuss this, he'd be like, "What are you talking about?"
You did a lot of computer in your presentation. You had also many calculations, graphs, and simulations. Well, in what program you used to make this tension graphs, the gravity tension? If you said that gravity can be something like tension and torsion, so did you use a specific program to simulate?
Are you talking about the vector graphs? The graphs of the vector? Oh, right, yes. So that is, I use Python.
Python.
Yeah, and then but the actual graphing library in the Python is Plotly. So that was I really like Plotly. I think they're great, and they make great graphs.
You can do your computational physics, no problem. And in the same time also, you talk about new theory. Even if you use computers only for computational physics, you use computers just to make the model. Like I use my animations in my.
Well, this is it. I love using computers for models. I just think that's been my big thing for a long time, and I'm
Can I ask Rajan a last question, because I have to go? What time is it?
Yes. No, that's fair enough.
I want to ask Rajan something.
Yes, go ahead.
Because Rajan is more an expert than any one of us about general relativity. Yes, Rajan, I want to ask you if is there some analogous mathematically in the theory of general relativity, the same as Christopher describes? Is there something like quantum tension or quantum torsion? I mean, I think it's about tidal. It's quite tidal waves must be this thing.
Yeah. See, he talks about P, right? The surface tension. And Einstein talks about the stress tensor.
Oh, yeah.
When you are going through that, I think there is a connection.
Great.
because he talks about the when you do the general relativity equation, Roché tensor and all, it connects to a T, which is a tensor, and that contains the gravity, all those things. Is essentially the stress tensor. That is the stress tensor is connected with your surface tension.
Of course.
So,
but
we don't know the volumetric or surface. That's all.
So you must use that in your thesis. That there's what you're talking about tension and torsion is actually what is referred in general relativity as what Rajan said about the tensor, the stress tensor.
Yeah, but this is it. But I'm actually not writing a thesis on this subject, though. I'm doing a thesis on anomaly detection using different machine learning algorithms. But interestingly enough, I'm actually thinking about using general relativity in that to solve some problems. We'll see, might be something I'll do later on.
And Rajan, is there any prediction in general relativity about the speed of propagation of this kind of tension forces?
Yes, actually, Einstein, if you look at original Einstein's equation, he doesn't preclude the idea of faster than speed of light. The only thing he says is that it becomes imaginary. So he doesn't want to consider that. Actually, he limits, and he's correct about that for particles. Like you said, Emmanuel, that the particles will have only speed of less than speed of light. So that's true with particles, right? Yeah. So what happens in the imaginary level? Einstein doesn't want to talk about it. He doesn't like the spooky exchange of distance. Yeah. So he said that's, but he doesn't preclude that. Other people interpreted Einstein and saying that, it's an interpretation of Einstein. Einstein himself didn't rule out that. But they're talking with that and that people that in the real universe, because they were considering the observable universe where you can test the idea. You see, all the people, the astrophysics, they test the idea. That's how you prove the physics, right? That's what Einstein was trying to do. But he didn't get a Nobel Prize because it was not proven that generally he got special relativity. So he was trying to find a proof for general relativity. So is that proof is possible only in the observable universe. So hence he has to assume, the speed of light is the maximum. That's for particle. But his actual calculation didn't rule out the possibility of faster than speed of light. So people started.
I believe also that there is some gravity acts has a component which is longitudinal and acts instantaneously. I believe that, and LIGO doesn't in my opinion does not disprove this, because LIGO just measure the far field transverse waves. You don't bother to measure any longitudinal stress forces and how they propagate. But I definitely believe that gravity has some longitudinal component which is much faster than the transverse waves that LIGO measured, and they actually also agree at sea. The transwave deformations of space. But the space, if you accept it's not nothing, it's some kind of, and it's not incompressible. No, it's wrong. It's not.
It's for us.
Yes, it's not, because if it was incompressible, it will not allow any longitudinal forces to propagate. Incompressible means you cannot have pressure. That's pressure incompressible. So water is not. It's wrong. Even water is nearly incompressible.
It's
not just not perfect. It's nearly incompressible. But if you have an absolute perfect incompressible medium, you cannot have longitudinal waves, pressure waves.
Okay.
So
yes, I understand.
But vacuum, I believe, is not perfect incompressible. So there's a small component that can actually you can have pressure waves, longitudinal.
Yeah, of course you can have pressure waves in water.
Yes. So they're not just transverse gravitational waves. that LIGO measured. That's correct. They're going, especially for the far field, they're going definitely far field. What is far field? Is far field if the distance is many times the wavelength of the distortion. That's we call far field.
Okay.
Near field is the distance when the transmitter and the receiver are within one wavelength. So, for example, if you transmit say 2 megahertz signal, radio signal, 2 megahertz translates to 150 meters in wavelength. 2 megahertz, if you could do the calculation, c times the wavelength times the frequency, is 2 megahertz is 150 meters wavelength. So you have a sine wave, which is 150 meters in length. Yes. So if you put your transmitter and receiver within this wavelength, you say that this is a near field interaction. But now we're talking about galaxies which are 13 billion millions away. The gravitational wave was just had a period very small. I think 200 microseconds, something like that. So this puts it immediately to the far field.
Yeah, for sure.
The wavelength is very smaller than the distance.
Yeah.
They say that the distance happened 1.3 billion years away. The first detection of the LIGO, the distortion happened of the two black holes of the merger. The black hole merger happened at a distance 1.3 billion light years away, if I remember correctly.
But how big is the wavelength?
Yes, the distance. No, it's not the wavelength. It's the distance of our planet from the source of the distortion, where in the space where the two black hole merger happened.
Yes, but those wavelengths would be like really small, can't they? The blip would be really big, can't they?
It was not big. It was very small. So it has a very small wavelength.
Yes.
The blip was.
Yeah.
The whole time was about, if I remember correctly, no, it was not it was not microseconds. It was actually 200 milliseconds. So do the calculation and see in what wavelength this corresponds.
It's very small. Yeah. I think it's smaller than their detector will allow because it's because of how it's like small.
That's exactly the distortion in the LIGO detector was 1,000 times smaller than the nucleus of a hydrogen. I think they say that. They actually measured that within the thermometry. Yeah. That's what they measure.
It's impressive technology, and it's obviously a signal to noise ratio would be off the charts on that one, Rajan. Yeah.
Yeah. So what are things is
about signal to noise? Yeah, they say that they compensated for that. They compensated for every parameter, even the noise. Yeah.
Yeah, it's impressive engineering if that's the case. I mean, they've detected so many of these things now that really who can argue with them?
Yeah, they detected also a neutron merger, and there was actually optical confirmation in the second case. There was a neutron star merger, not a black hole. But in the same time, they saw the light also coming from the merge of the neutrons. There was not only gravitational confirmation in the second case. You had also optical via the telescopes. They saw actually on the sky the event. They saw gamma radiation coming and all that stuff. Yeah. So they could verify that, and they both signal, both the gravitational distortion and the light signal from the merger came up at the same time, almost.
Well, that's the same speed.
So it's a speed with speed c, yeah, that's it. But this is a transverse distortion. Yes, you see. So when you have, because near field interactions are longitudinal, this kind of longitudinal interactions are only near field. They die off very quickly. Longitudinal dies off very quickly.
Right.
The transverse component which is much more far field.
Okay.
Stable, no?
That's good to know.
Unless you have a frequency, an event which produces a frequency of 0.1 hertz, very low, then you will not see this component. This longitudinal.
I see what you mean. Yeah.
And that's why in my experiment I'm in the near field, because I'm using 2 megahertz signal.
Yeah.
And I just have 1 meter separated my transmitter from my receiver. and the wavelength I'm observing is 2 megahertz. So it's 150 meters over 1.5 meters. So it's 100. The distance between the transmitter and receiver is 100 times more than the. So the wavelength is 100 times more than the distance between receiver and transmitter. So I'm in the near field. Yeah. That's why I could measure. If I would separate more my two antennas, I will not see the superluminal effect.
Oh, okay. So
Emmanuel, I want to clarify one thing. The near field, the lambda, the wavelength goes to 0, right? So what happens then?
Yes,
then it will immediately become superluminal.
R over lambda, where R is the distance between transmitter and receiver, over lambda, which is the wavelength, goes to 0. Yes, goes to 0.
Yeah. If lambda goes to 0, then that becomes infinite, which means immediately near field becomes far field. Immediately it becomes superluminal. Is it possible? The near field, when the lambda goes to 0, the near field immediately becomes superluminal. Because
yes, that's a very good explanation. Yes, actually, they go and read the papers of a guy. I forget now William Walker. William Walker has explained why the near field radio transmission is superluminal. It's not linear. So it's in the far field, it's always linear and equal with C. But as you go closer to the source, if you put the transmitter closer to the source, the phenomenon becomes Dr. William Walker. Look for his orthography. Make a superluminal Walker, like Johnny Walker, you know, WL the whiskey, WALKER.
Very similar.
William Walker, and put superluminal support. You will see many very interesting articles he written about the near field superluminal phenomenon in the radio transmission. Yes.
The other aspect I want to bring is, about the oil, and you are dropping the oil into the surfactant. You are putting that black hole.
Yeah, but Christopher is not. She's coming just because Christopher Rajan will ask you something about the black hole.
So, the Marangoni effect. It's like Emmanuel pointed out, and you had excellent discussion. Both you, Emmanuel, and Christopher. I really like it, discussion and the debates. I think it clarifies a lot of things. But one question, one of the things I want to, a unifying conjecture if you want, is that we consider, like I published with Emmanuel about that first model, about superluminal thing, where I talk about, the two things after Helmholtz decomposition. One of them is, in terms of the physics, it produces micro black hole and also 0 point, right? These are the final things. So I feel that drop you're dropping, right, for the Marangoni effect, you're putting a drop there. That drop could be a micro black hole in a 0 point vacuum.
Well, because the way I'm saying, like, there's ordinary space, which has a gravitational constant, like a surface tension of Newton's G constant. And then surfactant space is like another kind of space with a different gravitational constant. So it'd be interesting. Like you could build an entire universe out of surfactant space, and you could have black holes in it, and you could derive the physics
that's what
in there. But any of that, if you transport any of that universe into this universe, it will cause, because of the particular surface tension gravity of that space, it will cause all of surfactant space to like move away from it, and it will expand. And the reason why it expands is because ordinary space wants to maintain its cohesion. It wants to survive, essentially, and that's what happens.
So I'm just explaining that the actual thing.
It's like a reverse black hole. It's more like a big bang happening on the surface of the sphere. But the big bang happens happened according to this model. It was kind of a full. It was all like a show, you know. Like as the thing rotates, it's just like it's like a disco ball reflecting on the surface of a dance hall. It's like it looks like it's moving.
Yeah.
It's actually moving.
Christopher, you have to clarify also that when you say surfactant space, you are referring to ordinary matter. That's right?
No, not at all. So I'm saying, so ordinary space is the space we live in now with and the matter
vacuum, including the vacuum. Yeah. Okay.
Yes. Yeah. All of
Sorry.
So this is it. This substance, right? This proposed. It could be a. I mean, well, I don't want to get into that aspect of it just yet, but it's like a separate thing. And if it was here, it would cause the destruction of our universe. So the fact that it hasn't arrived yet means that it either doesn't exist or it hasn't been brought here yet. So it implies that when it comes, it won't be an accident. It will be put there deliberately. So that I think is interesting.
Let me ask you two questions, and then, guys, I must go. I really enjoyed your conversation, the three of us. And where did Gert go? I lost him.
Gert sent me a message. I think he was like, "Oh, it's time for me to ask questions. Better go." And he just sent me a message. I've got to go. And so he left.
Because he didn't talk, and then I thought, where is he?
Yeah. So, well, I couldn't wait goodbye to him. I thought everyone could see the message, but then I checked and I saw it was just a private message to me. So
okay. So two questions. I want to make the last questions.
Yeah, sure.
My first question: why you think that the surfactant space is what the ordinary matter with vacuum? And not just say now is the Occam's razor. Why you don't just say that surfactant space is ordinary matter, galaxies, light, all this energy, light, luminous energy, and the vacuum is the other space, the oil.
No, I think I think you might be getting I'm trying to explain this as best I can, but you might be getting a bit mixed up. So if the pepper on the water is the matter, the water is space, and and water has a surface tension, which is the gravity, and and that surface tension is measured by Newton's constant G. Now, if we have another substance called washing up liquid, for example, and that has a different surface tension, different space, because it has a different gravitational constant. When we merge the two together, then we have the Marangoni effect. So it has to be two different kinds of space. So we could do it even without the matter. We could have no matter in the universe, and we could drop a bit of new space into ordinary space. And we'll have the same effect. We just won't be able to trace it. We wouldn't be able to see what's happening. And it would have no effect.
If you imagine now that we have space, vacuum space is the oil.
Yes.
And then you drop this pepper,
Yes.
Surfactant.
No. There's not a surfactant. Just pepper.
Okay.
Just pepper, the dry pepper. Will
it
not spread out? It will not spread out. You will not have the Marangoni effect if you put it in a blob of water, a blob of water, a blob of oil, or blob of soap. You sprinkle some of this pepper stuff. It will not produce the Marangoni effect.
I don't believe you would. Maybe a small one or something, but I mean, I'm not an expert in this field at all. But all I know is that you could have, like, most of the experiments are done with the pepper mixed with oil and water, so it's like all together, and then you drop the surfactant in. So, and I think they use the oil as a kind of a tracer. It's like easier to see what's going on. In fact, it's interesting you brought up the idea that, and thanks for the compliment, that I'm looking at observational things first instead of mathematics. It's actually fairly true, because I was in my kitchen and I was actually supposed to include this experiment in the talk. I was going to have my phone and videotape it, but I completely forgot. I had so much on my mind with the presentation.
Okay.
So,
the video was also impressive. Yeah.
Yeah, so I was like washing a pan full of oil and water, obviously.
Yes,
and there was like bits of food in there, obviously, as well. It was like, I don't know, I did a stir fry or something, so it was red. And there was all this oil particles. And then I just got a tiny bit of washing up liquid and dropped it in at like one side of the pan while I was moving the pan like this. And it all moved into like the far side of the pan and into like a spear like shape.
Yeah, it's surfactant. Yeah.
Right. So that was the tension. And then I thought, I was like, oh, that's how the universe will end. It's like, it'll be like this addition.
You had an apocalypse moment. You had it's like the apple, you know, bong.
Yeah, I was like, oh, that's it. Because like it was all based, it was all coming up. I was like thinking about the hypersphere and all this, and I was like, great, yeah, we have the beginning of the universe, and then I don't know, there was a couple of other thoughts, but then I was like, oh, this, and then I was like, oh, so this is other space, and then you see somebody, yeah. If space has a graviton associated with it, like if gravity has a particle called a graviton associated with it, and surfactant space could have a different kind of graviton associated with it, and dark space, would have a different graviton, which would be the dark matter particles. So we don't have to get rid of dark matter to have dark space. We don't necessarily need dark space.
Imagine the other scenario. Imagine also the other scenario. You have a vacuum space, which say it's the oil, or the mix with this, or mixed with oil and water, whatever.
Okay, yeah.
And then from a process we cannot understand, you have in the center of the blob, which is oil, which is the vacuum, I say.
Sure. Yeah.
You have a phase transition of matter, and you create a different matter, the surfactant in that case. In your case, the surfactant. This will then also spread. Yeah. So you have two different substances. You have actually one substance, but the same substance transitions has localized in some points of the whole blob, which is the whole. You have a phase transition of matter. It becomes something different. But because
I think we might be getting a bit confused, because obviously when we're talking about water, oil, washing up liquid, we're talking about substances. So that's matter. But I'm saying that there are three types of space that are like, we could use the three types of matter as an analogy for these three types of space. And then within those three types of space exist matter, all the matter that we know of. Yeah.
But I'm saying that you don't need three different times of. I say that you just need two.
We could just have two. Yeah, no, I'm just
one.
Yeah,
one.
That's why I'm saying
locally you have a phase transition of that one matter.
Well, wait a second. So when you're saying two, you just mean ordinary space and surfactant space. Like we don't need the dark matter space.
Yes, I say that in the beginning. It was just the expansion, the inflation of the vacuum itself. There was no matter.
Oh yeah.
Only in the Big Bang, the inflation phase, within a fractal of picosecond, you have the inflation of the vacuum, not matter. There was no matter.
Well,
and then the vacuum phase transition to energy. It has because the vacuum is, in my theory, superluminal energy. But then the vacuum itself had a phase transition to a different matter, which is ordinary matter. But if you have this volume of vacuum and you have only a blob of matter, then you can use the Marangoni effect to explain how the galaxy formed and spread out uniformly in small blobs.
Right.
Okay.
Yeah.
So it could very well be a false vacuum, a true vacuum, and a false vacuum.
No,
Yes.
I wouldn't get confused between true vacuum and false vacuum, because those are different topics.
The false vacuum is the saying that the vacuum has now 0-point energy, which can measure 10 minus, but it can drop in the future to a lower value.
Yes.
And when this happens, then we are screwed.
Yes.
No, but
you know,
that's
my point is that
different to what we're discussing on the terms.
This could be your surfactant space.
Yeah.
Your surfactant space could be the false. Let's say that's a false vacuum, surfactant space, and that falls into the.
I think they're very different. I think they have very different properties because I did outline what the gravitational constant of surfactant space is, and as far as I know, we don't know anything about false vacuum. The false vacuum. It's like if it exists, we're in a metastable condition here. The top quark is about here, and then this is the false vacuum. It could just go on forever. There could be no end. There could be no parameters. We don't know.
My conjecture is that false vacuum, micro black hole is the false vacuum. Micro black hole.
I mean, what is micro black hole? It's like you get two particles smashing together, you get a micro black hole or something, and that is a false vacuum. Is that not just like matter? I don't know.
The center of the micro black hole. Look, the false vacuum is now what we are in.
Oh, I see what you mean. Yeah. Empty real vacuum.
The true vacuum is if you fall in a state where the vacuum is even more void, even more. The 0 point energy is even more or less. When this happens,
so I don't know about that side of things. Like, is the surfactant space equivalent to more void? Is it more void than our void? I don't know about that. Maybe it's less. It's probably it's supposed to have a lower gravitational constant anyway, and that's about all I can say about it. Beyond that, I was thinking that we could chain the 3 kinds of space with the 3 generations of matter. So electron, tau, and so something like that.
That's interesting. Yeah,
but the order is wrong because it goes. I'd have to think. It goes ordinary space, dark space, surfactant space, and those go down in strength of gravitational field. But if we look at the what is it? Electron, neutrino, tau, and muon. Getting them mixed up. Tau, neutrino, tau, electron, and
it's electron, muon, and tau. Electron, muon, and tau.
Sorry,
tau is the heaviest, and tau is the heaviest, then it's.
So tau is the heaviest, and so basically, they're out of sync because our universe should be made of the muons, I think, or they should be made of the taus.
Muons is heavier.
My notes.
Electron is the lightest. Then comes muon, which is the muon is about 200 times more massive than the electron, and then it's the tau, which is even more massive than the muon.
So when I looked into it, I was really hoping. I was thinking, oh, this would be a cool way to explain everything, maybe. But then I was like, it just quite doesn't work out, to be correct. There's it just doesn't join up.
Yes, if we sometime in the future transition from if such things exist and we are not now in the false vacuum, and then we transition to the even more vacuum, then we are screwed up because it changes the fine structure constant immediately.
Oh yeah.
The fine structure constant will change, and the matter cannot exist in the form we are known now. So we are screwed. So this was my first question. My second question is I didn't understand about this 2 hours and 30 minutes that the end of the world will occur. And so the whole universe will obliterate.
Yeah.
You calculate exactly 2 hours, 30 minutes, and for where I was surprised.
No, on a 24-hour basis, right? You are talking about a 24-hour basis.
Yes.
24-hour basis, it will be that, right? That's your basis.
But
the vacuum, they say if the vacuum collapse occurs and we transition from the fake vacuum to the more void vacuum, it will propagate with the speed of light. So even if say 1 billion years an event occurs and you have a hole in the vacuum which is more void, something like it will still need 1 billion years to reach you. But you're saying that the whole universe will obliterate in a matter of a couple of hours.
Yeah.
Because it's also my theory. This is not my theory. I have a similar theory
Great.
that the vacuum will collapse or everywhere at the same time.
Wow.
Everywhere. Instantaneously. My end will be a big flash.
Oh,
because,
yeah, I've heard of that.
Yes, because the energy is superluminal. The energy is superluminal. We cannot see it. Now we say it's nothing. But the graviton spins and then it loses energy. And when it transitions from superluminal rotation to luminal, it will convert to light. So the whole universe will end to a big flash. And because the light is energy, it will again gravitationally pull again to a singularity, and then boom, boom, like a heartbeat. So my end is not the end; it's a cyclic Big Bang.
It will, but doesn't it take like a ridiculously long time for that to occur? Something like
yes, very ridiculous time.
Yeah, like
calculated it.
Yeah, I remember I read that paper.
Because now the speed of the graviton, the rotation, is 113 orders of magnitude larger than the speed of light, if I remember correctly. Maybe. So it loses very small. It's a universal ticking clock. It's actually what creates time, the rotation of the graviton ring. So it loses very slowly time. It will take billions, a Google number of years to go to luminal speed. As soon as it transitions to C, all the vacuum, this superluminal vacuum energy we perceive now as nothing, will translate to light, and we will see a big flash of gamma radiation.
And so did you come up with the term big flash then, or is big flash a...
It's a big flash. It will create an enormous enormous volume of energy.
It's a great name. I'm just wondering, where does the term originate? Is it part of the collection of, big crunch?
Big creep, big freeze and all that stuff, big crash.
I'm gonna have to change mine to big flow or something to fit in with you guys. I know.
Big flash. Big flash is nice because the idea is that all the energy of the vacuum, the hidden energy we cannot see, will convert to luminous energy, and this energy, of course, will have gravity, because according to Einstein, energy equals mass. So if you have a lot of light energy, it translates to mass, and mass has again gravity. So it will then come back, shrink to a singularity, and then produce the next Big Bang.
Okay. So if you have enough of this light, it will create the matter, will it?
I repeat again, Christopher.
If you have enough of this light, you basically have a Big Bang anyway. But it wouldn't be in a singularity, though. It would be spread out everywhere. That's what I'm worried about.
No, but photons, right? Photons can collide with each other, right? There is nothing. I mean, a photon go into each other, so everything becomes a light. It becomes photon. They flow into each other easily, right?
Yeah.
Bosons.
The photons can move into each other.
Yeah.
There is nothing. Yeah. So that's the property of the photon. So they'll keep moving into each other at superluminal speed until that's why I'm talking about. I think there's a mechanism I will call right now, maybe more than that, condensate mechanism. So you have evaporation and condensate. This is what keeps us alive, like source sink mechanism. So you can call it condensate source sink mechanism, something like that. As long as that keeps going, the universe will go in. Only if something interrupts that mechanism, right? Somehow, then you have the problem that Emmanuel is talking about, the problem that Christopher is talking about. I think that's my.
Well, I don't know if you have the same problem that I'm talking about. I can't talk for Emmanuel there.
No, different. You are talking about two different things, and so
I don't disagree with your conjecture there or your proposal about the source sink, and John also talks about it. I think like you could even have energy flowing in from the outside the hypersphere onto the sphere.
All that. As long as that keeps going, right? That I call it the mechanism. the super.
Yeah, but there's other factors involved. Like as long as the light, the light at the projective point continues to shine, the universe will continue. As long as the tangent plane continues to exist, the universe will just go on and on.
In my case, in my model, the gravity I'm describing, this ring of superluminal energy, which is I call also the dark energy, is cold. It's the first cold boson. It's not translating. It's not a tachyon. It's cold. It's the only cold boson. You know, boson translate always with a normal speed. I mean, photon is a boson, and it goes only with c speed. In my case, if not forced to, it can displaced. So imagine like water molecules, they stay in place unless they get for some reason displaced. Yeah. So in my case, imagine the superluminal ring is rotating very fast, superluminal, but it is not translating. It's not a tachyon. It can stay in place there in Cartesian space. Free, but it's just rotating very fast.
Yeah.
That's my model.
Very similar to a hot PDP. You talk about
tachyons, yes.
Yeah. We talk about. You know the Emmanuel, you probably know. I mean, in one of the things we talk about hot PDP mechanism in one of the papers.
I don't think it's anything like that though, because John's Hod thing travels very fast. So
no, I don't believe in tachyons.
No, Hod also.
I believe it's like water. The water molecules can stay there where they. I mean, they can have a Brownian motion. Yeah, the water molecules, but they're not translated. They can, because bosons always have to fly away, you know, the bosons. But in case my graviton, which is the only elementary particle, which consists all the vacuum, is the vacuum elementary particle, and also the matter, but because everything consists from gravitons. In my case, it can't be cold.
It can be cold.
Cold means it does not translate. It's not forced to.
Yeah, because it would have no energy. Yeah.
Okay. In the largest sense. Yeah.
Imagine
the largest. Okay, go ahead.
You remember my presentation about the flux line? The flux line.
Yeah.
Like we have in the magnet, the flux line. So the flux line the flux line is just cascaded gravitons, aligned gravitons. Yeah, you remember? And they have an outer skin. This graviton has this superluminal energy. But we cannot observe this energy. But the graviton has an evaporation mantle, a skin. This is the flux we see. So the flux line actually is hollow inside. It's hollow. You know, it's a ring, and we can see only the mantle. This is the flux. Inside the graviton is a ring. The ring inside is completely void. It's the true vacuum. That's what Rajan said about the macro black hole.
So like the macro black hole, with the ring, where the vortex is going,
it's the true vacuum. The vacuum, what we see, is just the 0-point energy, which is the skin of the graviton, the evaporation project.
That's interesting, because if there's a true vacuum, which in my case would be, you know, whatever exists in the fourth dimension. Like, so if you were to remove what's here, and then you'd have what's in the fourth dimension.
You can call it hyperspace.
I'm kind of thinking about matter in terms of a fourth dimensional thing, especially when I'm talking about that surface tension gravity, which might permeate into the center. You need a 4-dimensional geometry. Now that could be wrong, but I just think it's interesting to link it that way. That I think actually, sorry. I would say that that's not wrong, because even if we look at, well, I mean, not completely wrong is what I'm trying to say, because even if we look at general relativity, they're using effectively a projection of a Riemann hypersphere, which is 4-dimensional to create the curvature. So even in general relativity, although it's never stated publicly that I've heard before, they're modeling matter as a 4-dimensional object. So I kind of think I'm onto something with that.
Yes, I agree.
Go ahead. One more thing. Okay.
The Riemann sphere. Yes, the Riemann sphere, and also what is the other sphere, which is also very important.
Block sphere.
The box sphere. Yeah, the box sphere. The block. Yeah.
Henry Block or somebody. No, what's his name? No.
The Block sphere, yeah. The Block, exactly.
Yeah, I don't know his first name, but that's
BLOCH, right? BLOCH.
I mean, they're both using complex numbers. They're both using complex numbers. Yes.
Yes.
So you have a real part and an imaginary part.
Yeah. It's related to the
rotation.
Polarization of light as well. I think you can do a Block sphere with light polarization, which is another interesting thing, because I'd be interested, could there be polarization between the from the magnetic monopoles between the curvature of the hypersphere and the tangent plane, and could that create something?
That's a good question. That's a question you can investigate. Yeah, but I mean, because Rajan said about something imaginary that general relativity accepts, does not reject superluminality, but they say just imaginary, and they make the connection directly with tachyons, which are translating always to the. This is wrong for me. I mean, in my opinion, it can be a cold superluminal particle, which is only rotating superluminal, not translating. But these imaginary components in the Block sphere and also in the Riemann sphere are actually rotations.
Right. That makes sense.
The imaginary component of the complex number, which is represented in the Riemann sphere, is actually an angle, a rotation angle.
Yeah, of course.
That's why I'm saying
could be Euler angle.
The imaginary superluminal particle must be represent a rotation, not a translation. Must be. That's exactly the meaning we get from the Block sphere and the Riemann sphere. That the imaginary component represents rotation, not translation. So that's why I'm saying that the general relativity is correct. Yes, if it accepts superluminality and says it's an imaginary particle, it must be a rotating particle, not a translating particle. It can be. It will be called translating. It will not translate, but it will be superluminal rotating. It's spinning like a hell. No?
Yeah. I mean, that kind of links back a little bit in a different way, albeit to the magnetic monopole ray, because that rotates.
The monopole is a ring, yes.
Well,
so
but even
rotating,
it's just a line, like, so if you're looking at if you're looking at the line, if you're looking at, like, let's say a line straight on and it's rotating in one direction, then you have a north pole. But then if you were to turn it around the other way and keep the rotation the same, it will look like a south pole. And so those two.
Yes. You know what you mean. Profile and face off,
Yeah, because you know the way, I think you showed the video before of the I forgot what the solenoid, is it? Where it's connected by the tube, and then it's got two vortices which are rotating in opposite directions, but they are one thing, and that is a model of a monopole. So the monopole is actually like a line in a sense. Well, it could be a ring. Yeah, I see what you mean. Yeah, it could be like a hollow tube ring, but it could be so tiny that, like,
of course.
Kind of
We're talking now about sub-Planck length. Sub-Planck. We're talking about sub-Planck, not just Planck length. Subdivision, division of Planck. Yes. No, it must be. Up to the Planck length, you have light.
I'm just not that expert, so I can't talk about that.
Up to the Planck length, you have light. You have light space-time.
If
you want to go superluminal, and you believe that there is no such thing like infinitesimal small, but there is always finite value of something, of sizes. It must be the graviton must be sub-Planck size.
So the possibility is that, you have monopoles, right? The monopoles, they exist in the superluminal thing. Okay? But when it becomes dipolar, now they become vacuum and subluminar. So the dipole cannot exceed the speed of light. It cannot go faster than the speed of light.
That's actually the phase transition I'm talking about in the Big Bang. So you had the vacuum, and the vacuum had a sudden phase transition. Like, water to ice and ice to vapor, water to vapor. So this kind of phase transition. So the vacuum, suddenly something happened, and some components of the vacuum lost their superluminal energy and transitioned to luminal energy. But luminal immediately translates also to ordinary matter, because then you can have also subluminal speed or energy, and then you end up with matter, because matter is subluminal energy, subluminal.
Yeah. And that only can be dipole.
Yeah. And this happens
only dipole.
Yeah. The graviton is a monopole, and when it comes, for some reason, if it collides with another and loses its speed, it will transition to normal space-time, Einstein space-time, and will form dipoles.
Dipoles.
Yeah.
The dipole.
I believe the first.
That's what HOD is. The HOD is the dipole. HOD is the dipole.
The electron is a dipole. I think that the electron is actually made from two dipoles in the Big Bang. First,
Good idea.
Of magnetic monopoles, a soup, and then they came together and formed the first dipoles. And from then, the rest is history.
Yeah, it's a good model. I like it. Okay, I'm going to end the stream there.
Okay.
Yeah, I really enjoyed, but you still only calculation.